Here's a question for you. How many people does it take to turn on a light bulb? The answer seems simple. Just walk into a dark room, flip a switch, and instantly you can see, right? Well, the truth is there's a lot more to generating and delivering electrical power than you've probably imagined. Hi, I'm Lee Patrick Sullivan with Energy Now, and this Energy 101 video explains the system used to generate electricity. And it also explains what it really takes to turn on a light bulb. In order to understand energy, we first need to start at the source, literally. Mother Nature provides the natural resource we use to generate power. From natural gas to coal, ocean tides to mountain winds, the energy we need to create electricity must first be mined, harnessed, or collected from the earth. Some of these resources are finite, including fossil fuels like coal and oil, but others are unlimited, like solar or wind power. But a lump of coal or a strong breeze alone won't create the power that turns on your light. For every energy source, a chemical or mechanical process is required to turn it into usable electricity. Every day, researchers work to find innovative ways to use our limited resources, process raw materials, harness renewables more efficiently, and find entirely new energy sources. Today, the majority of America's electricity comes from thermal power plants. Fuels like coal, natural gas, biomass, and uranium are used to heat water until it produces steam, which powers a turbine and generates electricity. That steam turns propeller-like blades around a rotor inside the turbine. This turning rotor connects to a main shaft which spins magnets with a coil inside a generator. It's the generator inside a turbine that converts mechanical energy into electric energy and creates electricity. Steam is an efficient method of producing electricity because the water can be recycled and reused as it changes back and forth between liquid and gaseous states. Transporting electricity from the power plant to your home is an entirely different process. Current technology cannot cost-effectively store large amounts of electricity, so significant challenges exist when it comes to transferring that electricity across long distances. Just enough electricity has to be generated to meet demand at all times and be transmitted through power lines to reach your light switch. Too much or too little power can crash the transmission system and cause a blackout. That's why a complex mix of logistics, management, and infrastructure is needed to transmit electricity from power generators to consumers. Enter the electricity grid, also known as simply the grid. The North American electricity grid is actually made of 4 large grid systems: the Western grid, the Eastern grid, the Texas grid, and a grid covering the Canadian province of Quebec. These independent regional networks of power plants and transmission lines carry electric energy at high voltage within their area to local utilities. There are very limited links between the 4 grids, which means electricity generated from a wind turbine in West Texas cannot reach an apartment building in New York City. For electricity to move through one of the 4 grids, its voltage must first be increased by a device called a transformer. Then the electricity can travel long distances across high-voltage transmission lines. These high-voltage lines are generally strung between giant metal towers. They stretch for miles from power plants to local substations in each neighborhood. You've probably seen substations along the side of the road and wonder what they do. Well, their job is stepping down electric voltages from levels as high as 765,000 volts closer to the 110 volts you use in your home. The electricity from the power line on your street passes through another transformer, which steps down the voltage once more, and then it travels along the line into your house. From there, the electricity enters your breaker box, and it is then distributed to light sockets and outlets. All you have to do is flip a switch. So, as you can see, from the raw materials to the power lines on your street, there's so much more to the electricity ecosystem than meets the eye.
Hi, I'm Lacey Lett, and today I'd like to talk to you about natural gas power plants. Many Americans use natural gas for heating their homes and cooking their food. But did you know that gas also produces about 30% of our electricity? And that percentage is expected to grow because natural gas has become the #1 choice for large new power plants in the United States. So how do these natural gas plants work? Well, they work much like the spinning turbine of a powerful jet engine. Burning natural gas at the power plant heats up the air needed to spin the hundreds of propeller-like blades in the turbine. The turbine is connected by a shaft to a generator that makes an electric current. By spinning magnets through a wire coil, it converts the mechanical energy of the turbine into electricity. That's why it's called a generator. This type of power plant is called a simple cycle gas turbine because, well, it's pretty simple. There's only one turbine and one generator. There's also a second type of natural gas plant called a combined cycle power plant. It combines a gas turbine and a steam turbine used in a coal power plant. But instead of using coal, or even more gas to create steam, a combined cycle plant uses the exhaust heat from the gas turbine to boil water into steam. The steam then drives a second turbine, which spins a second generator, producing even more electricity. This two-step combined cycle process is highly efficient, converting as much as 50% of the energy contained in natural gas into electricity. In comparison, coal-fired steam turbines are only about 33% efficient. And this is one of the main reasons why gas-fired power plants are better for the environment. Natural gas starts out with a lower carbon content than coal, and with more efficient power plants, it can produce electricity with about 60% less carbon dioxide than coal-fired power plants. Also, natural gas plants do not release many of the toxic substances like mercury that comes from burning coal. Modern natural gas plants can get going in just 15 minutes. That makes them ideal for backing up renewables, since they can switch on and off faster than most other conventional plants and partner with wind and solar energy as the wind changes or clouds move across the sky.
Generating electricity requires a fuel source. At this plant, the fuel source is coal, which arrives mainly by a barge but also by rail and truck. Each barge delivers 1,500 tons of coal, enough to keep the plant running for a couple of hours. The plant uses about 21,000 tons of coal each day, so over 1 million tons of coal is stockpiled next to the plant. A device called a stacker reclaimer scoops coal onto a quarter-mile long conveyor that can transport up to 900 tons of coal into the plant each hour. Once inside the plant, up to a 30-hour supply of coal can be stored in bunkers. Coal moves from the bunkers to feeders to be measured and moved to pulverizers. Each generating unit has 16 coal feeders that supply 8 pulverizers. Coal enters the pulverizer and spins in a large drum, where hundreds of steel balls grind it into a fine powder. Now a fine powder, the coal leaves the pulverizers and heads to the boiler. About 335 tons of coal can be pulverized per hour. Large fans add warm air to the powdery coal and blow it into the boiler. The boiler has miles of tubes filled with high-quality water. Once inside the boiler, the coal ignites, releasing energy and generating intense heat that changes the water inside the tubes to hot, dry steam. The temperature of the steam is now about 1,000 degrees Fahrenheit. This process generates thermal energy, which is transformed to mechanical energy at the turbine, which is the next stop on our tour. High-pressure steam, now 1,000 degrees Fahrenheit at 3,500 pounds per square inch, is piped from the boiler to the first in a series of turbines. Here it expands between layers of turbine blades mounted on the turbine shaft. The steam loops back to the furnace, then onto the second turbine. In this process, the steam turns the series of turbines 3,600 revolutions per minute, providing power to the generator, the last in the series of machines. The generator continuously creates an electrical charge of 34,481 amps at 18,000 volts of electricity. From here, the electricity leaves the plant and begins its journey to customers. After the steam has been used to create electricity, it is exhausted from the turbine and sent to a condenser to be changed back into water. Inside the condenser, steam passes over the outside of pipes filled with chilled water from the cooling towers. The steam condenses to water and returns to the boilers to repeat the steam generating process over again. As the steam condenses, the chilled water inside the condenser pipes becomes warm from the heat of the steam, so it is sent to a cooling tower. These particular towers are called natural draft cooling towers, which are designed with no moving parts. Inside, the water splashes over a series of baffles, which breaks up the water into small droplets. These droplets mix with air from the open bottom of the tower, evaporating some of the water and cooling the rest by as much as 27 degrees. The newly chilled water returns to the condenser to repeat the process of cooling more steam. Since 1971, First Energy has spent more than $5 billion on environmental protection. Our plants are equipped with air quality control systems to remove sulfur dioxide and particulates called fly ash. Fly ash is removed by a mechanical process, and sulfur dioxide is removed with a chemical reaction using lime. These processes take place in large ductwork scrubber trains located between a unit's boiler and its chimney. Boiler gases pass through scrubbing vessels and are sprayed with slurry, a mixture of water and lime. The sulfur dioxide particles and other pollutants are absorbed by the slurry and fall to the bottom of the vessels. A fan releases the cleansed gases through the chimney. By the time this happens, more than 99% of particulates have been removed, as well as 92% of sulfur dioxide. A plant similar to this one can remove over 400,000 tons of sulfur dioxide each year. The scrubbing process creates huge amounts of a byproduct called calcium sulfite. This plant could create more than 3 million gallons of calcium sulfite slurry each day. First Energy created a process that turns that waste product into a valuable building material called gypsum, which is used to make wallboard or drywall. The slurry leaving the scrubbers is thickened and pumped through a forced oxidation gypsum or fog system. Oxygen is then added, changing it into gypsum, which is dried, treated, and sent to a gypsum manufacturer to make wallboard. First Energy recycles about 500,000 tons of gypsum each year, enough to manufacture wallboard for 70,000 new homes. Precipitators are another method of extracting coal ash, also called fly ash, which can be recycled or deposited in landfills. This mechanical process extracts fly ash left over from the combustion process. These poles, called wrappers, shake fly ash from a vibrating wire. Gas from the furnace, containing fly ash, flows into the box. The fly ash drops into a storage chamber and is blown into silos to be loaded into a truck. Fly ash from First Energy plants is used in manufacturing a variety of products, including concrete, grouting, roofing shingles, granules, and anti-skid road materials. First Energy also uses selective catalytic reduction technology, or SCR, to reduce nitrogen oxide emissions. SCR systems work much like a catalytic converter on a car. Flue gas containing nitrogen oxide emissions from the combustion process is mixed with ammonia. The mixed gases travel through a series of catalytic layers, which causes the nitrogen oxides to react with the ammonia. The reaction converts the nitrogen oxides to water vapor and pure nitrogen, a benign chemical that makes up 80% of the air we breathe. Both elements are returned to the environment through the station's stacks. Now that we've taken a look at how electricity is produced and some of the environmental control protection systems used at our plants, let's take a look at how the electricity is delivered to our homes and businesses. Transformers located just outside the plant boost the power from 18,000 volts to 345,000 volts, so it can travel long distances over transmission lines to where it is needed. Substations located along the path reduce the voltage so it can be moved along distribution lines attached to the utility poles. As the electricity nears customer locations, transformers on poles step down the power for use in homes and businesses.
It all started with a big bang. Wait, we don't have to go back that far. The Earth was formed 4.5 billion years ago. No, still too far. Try this. It's the Middle Ages. People in Britain run out of firewood, start burning coal, but they use up the coal on the ground. Miners dig deep. Coal mines fill with water. Samuel Newcomen invents a coal-burning steam engine to pump out water so miners can keep digging. James Watt makes it practical for other uses. Now we have ingredients for the Industrial Revolution, fossil fuels, and a way to put them to work. All hell breaks loose. Coal miners bog down lugging coal. Rails make it easier. Rails and steam engine combined make a railroad. Michael Faraday makes the first electric motor. Nikola Tesla invents alternating current. Soon utility companies start burning coal to generate electricity. Meanwhile, Edwin Drake drills the first rock oil well in Pennsylvania, and Carl Daimler builds an automobile running on petroleum. Coal tar and oil are turned into industrial chemicals and pharmaceuticals that prolong life, more population growth. The Wright brothers start oil-fueled aviation. Fritz Haber and Karl Bosch make fertilizer from fossil fuels. Fertilizer and oil-powered tractors expand food production, feeding more people. World War I is the first fossil-fueled conflict. Then comes World War II, giving us guided missiles and atom bombs. In between is a Great Depression, partly caused by overproduction. Powered assembly lines make products faster than people need them. Advertising executives invent consumerism to soak up overproduction. It's the 1950s. Advertisers use television to hook new generations of consumers. In the 70s, there's an oil shock. Everyone's shocked to realize how dependent they are on oil. With the energy crisis, the environmental movement is born. But oil prices fall and everyone forgets energy shortages. There's a showdown between market and planned economies. Market wins. Goodbye, evil Soviet Empire. Politicians decide the market will solve everything. Personal computers arrive. Globalization takes over when the market notices labor is cheaper in China. Suddenly everyone has a cell phone, but world oil production stalls out. China is now burning half the world's coal to make export products. But where will China get more coal and oil to fuel more growth? Environmental problems everywhere. Rising CO2 levels lead to record heat waves, floods, droughts. Oceans acidify. Topsoil erodes by 25 billion tons a year from industrial agriculture. Ancient forests disappear. Species go extinct at 1,000 times normal rates. Fresh water is scarce or polluted. Oil companies drill in miles of seawater because the easy oil is gone. But a deep water oil platform explodes and fouls the Gulf of Mexico. Manufacturing moves to polluting countries where labor is cheap, while the U.S. becomes a casino. The financial sector is 40% of the economy. But Wall Street is over-leveraged. Banks fail. Unemployment soars. Credit evaporates. The economy is on the verge of collapse. Okay, present time. It's amazing how far we've come in 200 years, just 3 human lifetimes, from the beginning of industrialism till now. But where are we headed? We can't keep doubling human population. We can't keep dumping carbon in the atmosphere. We can't keep ruining topsoil. We can't keep growing population and consumption or basing our economy on depleting fossil fuels. We can't just print more money to solve the debt crisis. It's been an exhilarating ride, but there are limits. Now, it's not the end of the world, but we have to do 4 things fast. Learn to live without fossil fuels, adapt to the end of economic growth as we've known it, support 7 billion humans and stabilize population at a sustainable level, and deal with our legacy of environmental destruction. In short, we have to live within nature's budget of renewable resources at rates of natural replenishment. Can we do it? We have no choice. Alternative energy sources are important, but none can fully replace fossil fuels in the time we have. Also, we've designed and built our infrastructure for transport, electricity, and farming to suit oil, coal, and gas. Changing to different energy sources will require us to redesign cities, manufacturing processes, healthcare, and more. We'll also have to rethink some of our cultural values. None of our global problems can be tackled in isolation, and many cannot be fully solved. We have to prepare for business as unusual. Our best goal is resilience, the ability to absorb shocks and keep going. If we do nothing, we still get to a post-carbon future, but it will be bleak. However, if we plan the transition, we can have a world that supports robust communities of healthy, creative people and ecosystems with millions of other species. One way or the other, we're in for the ride of a lifetime. Understand the issues and pitch in. It's all hands on deck.